values, we have to find out the ICQ and VCEQ. Beta is given as 100 for the following circuit shown below. So here VB is written as, here VB is 24 divided by 20 into 10 that is, sorry, here VB is going to be 0 because of the exactly opposite and equal potentials. So, and Thevenin's resistance is going to be 5K. So if we model this circuit as, this is 5K minus 12 ohms, 2K plus 12 ohms. So apply the KVL at the input side. 0 is equals to IB into 5 plus VB, that is 0.7, and 101 IB into 2, and plus this is minus 12. So 12 is equals to 207 IB plus VBE, that is IB is equals to 12 minus 0.7 by 207 milliamps. So ICQ is nothing but beta times, that is 100 times 11.3 divided by 207 milliamps. So VCEQ is equals to 24 minus ICQ 4. So from this, ICQ and VCEQ is given as, here this is nothing but 5.459 milliamps. VCEQ is nothing but, it is, so 5.46 we can take approximately. This is 2.04 volts, that is option D is correct. For the NMOS circuit shown below, VTN equals to 1 volt, Kn dash is 30 microamps per volt square, and the W by L ratios are equal. So all the parameters of both M1 as well as M2 are perfectly matched. Means 5 volts is nothing but VDS1 plus VDS2. So both are perfectly matched, means they can handle the equal amount of voltages, that is V out is nothing but VDS2, that is 2.5 volts. Because they both are perfectly matched, VDS1 is equals to VDS2. So option C is correct. Circuit shown below, VZ is equals to 6 volts, VB equals to 0.7 volts, and beta equals to 100. Find the output voltage V0 is. Here this is 6 volts, means here also 6 volts. If across 10 is 6 volts, then across 20 is 12 volts. So complete V0 is going to be 18 ohms, that is option C is correct. Input Q is, here to A ground is connected. So if any one of the input is 0 for a NAND gate, the output of the NAND gate becomes 1. So Q is 1. Whenever Q is 1, for the below NAND gate, this is going to be 0. So Q is going to remain in 1 and Q bar is going to remain in 0. That is option B is correct. Shown in figure implements. So here, suppose if I am taking this as E. E equals to C bar, B bar, and C is 0, which is C bar, B bar. F equals to, here this is 0, this is 1. Here E A bar plus E bar 0, which is E A bar, which is nothing but F is A bar, B bar, C bar, which is A plus B C whole bar according to the De Morgan's law. So this is a NOR gate, that is option C is correct.
This is equal to s plus 1 by s plus 2. We have to find initial value of f of s. Okay. Now, what is f of s here? I can divide this one as s plus 2 minus 1 by s plus 2. So this is equal to 1 by 1 plus 1 by s plus 2. Okay, 1 minus 1 by s plus 2. Now, what is f of t? F of t is equal to delta of t minus e power minus t. Okay, to find initial value of f of s, that means limit t tends to 0, f of t is equal to, okay, it is having limit t tends to 0, delta of t minus e power minus t. Okay, when you go through the initial value theorem derivation, okay, initial value theorem is not valid for impulse functions. Okay, here f of t contains impulse functions. Since initial value theorem is not valid for impulse functions, the initial value cannot be determined, is the answer, option D.
Minimum phase system, the value of is, see, h of e power j omega is written as in z domain as h of z, h of z inverse. Here cos omega is nothing but z plus z inverse by 2. That is h of z inverse is equals to 5 by 4 1 by 2 z in z minus 1 by 2 z inverse. So which is written as to z. So if we do this one, z inverse to z and plus 1 by 4, that is 5 by 4. So if we according to the minimum phase system, all the poles are zeros, whatever it may be, they should lie inside the unit circle. So that is possible only for this one. So h of z must be 1 by 2 z in 1 minus 1 by 2 z inverse, that is option D is